Have you ever wondered where mathematics can be applied in engineering? Well, luckily you do not have to look too far. If you've ever driven in a car, you've probably heard the noisy rumblings of the internal combustion engine. The internal combustion engine consists of a series of mechanisms, one of which is known as the slider crank mechanism. The slider crank mechanism consists of a piston, a connecting rod, a crank, all contained within an engine block or frame as indicated by these lines. The name slider crank comes from the fact that the piston slides and the crank is this piece here which rotates about a fixed axis, hence the name slider crank mechanism. For this mechanism, we need to understand some basic maths concepts. Let's start with vector basics. A vector is something that has both a magnitude or a size and a direction. For example, symbolically, we often represent a vector with a letter with an arrow on top of it to also indicate that direction. The vector is drawn over here in a general coordinate system. The length of this line is the magnitude of the vector, and its direction is determined by its orientation. A vector can be broken up into components using unit vectors. Unit vectors are a special kind of vectors that are dimensionless and have a magnitude of 1. Basis unit vectors span any two-dimensional space. For instance, in this case, the basis vectors I and j, which span the xy coordinate system here, are indicated by these symbols with these caps on top of them. One form of vector calculus is vector algebra. The two main forms that we will look at include the dot product as well as the cross product. The dot product is a scalar, in other words magnitude-only result, calculated for two vectors. In this case we use b and the unit vector in the direction of a, or u subscript a. If you take the dot product between these two vectors, then you can calculate that magnitude or scalar value using this formula. The dot product tells us how much two vectors are aligned with each other. And we can tell this because if we had to take the theta value, which is the angle between these two vectors, as 0, 180, or 360, then this value would be maximized. In other words, when they're lying on top of each other, this value is maximized. It can also be used to find the perpendicular projection of a vector onto a line or plane in 3D space. For example, this dot product finds the projection of b in the direction of a. The cross product is the vector, in other words magnitude and direction, result calculated for two vectors. In this case we used a and b. It can be calculated by finding the determinant of this matrix. It looks like this. The magnitude of this vector can be calculated with a formula that looks very similar to the dot product, only now we use sine theta. The cross product tells us by how much two vectors do not align, and you might have already figured that out by looking at the sine of theta. In other words, when the angle between the two vectors a and b is 0, 180, or 360 degrees, then this magnitude of the cross product becomes equal to 0. And it also tells us how to find a vector that is perpendicular to the plane spanned by two other vectors. Let's take a and b for example. A and b span this plane over here, and if we take the cross product, then the resulting vector, whether it's a cross b or b cross a, is perpendicular to that plane. The direction of the cross product can be determined using the curl right-hand rule. Moving on to basic differentiation and integration, we will use the example of the piston's vertical position. Because it undergoes rectilinear translation, which is motion in a straight line, we only have to look at one dimension, which in this case is its position, y. If we take the differentiation of the position with respect to time, we get velocity, and if we take the differentiation of the velocity with respect to time, we get acceleration. You can also flip the arrow and move in the other direction by performing integration. Often these functions are quite complicated, and to simplify that, we make use of another mathematical concept known as the Taylor series expansion. The Taylor series expansion allows us to estimate a function's value at different points, or it allows us to simplify a function if higher order terms are negligible. The formula used for the Taylor series expansion is given over here. If we are going to use approximate values by, for example, using the Taylor series expansion, then it's also worth talking about error analysis. This allows us to evaluate the uncertainty or error of a solution to a problem. It also allows us to figure out what regions of input values allow our approximation to be close enough to the true solution. Let's take these two graphs for example. The red curve is the approximate function, whereas the blue curve is the true function. The error is essentially in this case the difference between the two curves. We can see that in some regions, especially low values of x, we see that that distance becomes very small. In other words, our error is less for these smaller values of x. But as we increase the x values, we can see the distance increases, and so our error increases. And for this reason, we'd like to be in the region where our error is lower. So what happens within an internal combustion engine with regards to the cider crank mechanism? On the left-hand side, you will see an animation of the cider crank mechanism in action inside an internal combustion engine, and on the right-hand side, you'll see a physical 3D printed model also showing the motion. The process begins when exploding gases at the top force the piston down. This causes the connecting rod to move, which then forces the crank to rotate. The crank is connected to the crankshaft, which then provides the torque necessary for driving the car forward. Let's look at each of these components individually. Starting with the piston. The piston moves in a reciprocating manner. In other words, it moves back and forth or up and down as shown in these videos. It also follows rectilinear motion, which is motion in a straight line. The piston is accelerated downwards during the first stroke due to pressure from exploding gases. The pressure is applied to the surface area A of the piston, which is shown over here, and then converts this to a force with the magnitude of the pressure times the area. The force is, however, a vector, as shown here by this arrow, and also has a direction, which in this case is pointing downwards. The force vector also results in acceleration of the piston, which results in acceleration vector, as shown here. The next component is the connecting rod. The connecting rod is known as the connecting rod because it connects the piston with the crank. The connecting rod undergoes general planar motion, which is motion that involves both rotation as well as translation. The purpose of the connecting rod is to convert the rectilinear motion of the piston into circular or rotational motion of the crank. If we look at a picture of a connecting rod from an actual engine, you might notice that it has a big end design. In other words, one side is much larger in diameter than the other side. This causes a shift in the center of mass towards the bigger end. The center of mass of an object is often taken to be the point where the entire mass of an object is assumed to be concentrated in order to make the visualization of its motion more convenient. The next component is the crank. The crank is connected to a crankshaft, which is coming in and out of this page and is shown over here. The crank undergoes fixed axis rotation about the crankshaft. The shape of the crank is quite interesting. That is because it has a counterweight that is needed to balance the inertia of the piston and the connecting rod. Here is where we can see an application of the cross product. For example, the torque is a vector that is calculated from the cross product between the position vector, shown in red here, and a force vector, shown in blue. This torque is what is transferred through various mechanisms to result in the forward motion of the car through the wheels. The pins are also very important components and are represented by these large dark circles. Pins permit only relative motion about a fixed axis, as shown in the sketch over here. The rotation involves angular displacement, or d theta, over time. And if we had to look at the rate of change of this angular displacement over time, then we will end up with the angular velocity, which is often represented by the symbol omega and has units in radians per second. If we had to take the time derivative of the angular velocity, then we will end up with the angular acceleration, which is often represented by the alpha symbol and has units of radians per second squared. Let us now look at the different vectors in the cider crank mechanism. But before we can do that, let us simplify our cider crank mechanism diagram. We can do this by first identifying the links and connecting them. The easiest way to do this is to join the different pins using lines. We then simplify our sketch by using simple geometric shapes. For example, the bars can be represented by straight lines, the pins just by circles, and the slider or the piston represented by a rectangular shape. The base or frame link can be represented by angled hatching lines. We can then label all the links and the slider as well as the pins. For example, we use the convention where we label the base or frame link, which is used as our absolute frame of reference, as 1, the crank as 2, the connecting rod as 3, and the slider as 4. Similarly, for the pins, we have at our origin, which is the pin at the crankshaft, labeled as O, the crank pin labeled as A, the piston pin labeled as B. After this, we then need to establish our absolute coordinate system. A convenient place for the origin of the coordinate system is at point O at the crankshaft. We then define the XY coordinate system by the basis unit vectors I and J, indicating that we've got Y in the vertical direction and X in the horizontal direction. Even though we are drawing all of this in 2 dimensions, we must remember that there is still a 3rd dimension in the Z direction corresponding with the basis unit vector K. However, because this mechanism is mostly planar, meaning it involves motion in one plane, we restrict our observations to the XY plane. But that does not mean that we won't have vectors pointing out in the Z direction. Let's now look at different types of vectors, starting with the position vectors. The position vectors are quite easy to understand. They often follow the pattern of the original diagram that we drew. There are 2 types of position vectors involved here. The first is an absolute position vector. For example, RA is a position vector of the crank pin A relative to the origin O. The position vector RB represents the absolute position vector of the pin B or the slider with respect to the origin. We then have the relative position vector. In this case, we have RB relative to A. This is the relative position vector of pin B relative to pin A, and is usually drawn in the direction going with this convention from A to B. Let's now look at some velocities, starting with the crank. If we had to trace out the crank pin or pin A and look at its path, it would draw a circle. If we then look at the velocity of that pin at any point in time, we will see that it can be calculated using the cross product between the angular velocity of link 2 with the position vector or absolute position vector of point A. The direction of the velocity at point A is determined by the direction of the angular velocity here. For instance, if the angular velocity is in the clockwise direction, then the velocity vector would point in this direction. If we move on to acceleration of pin A, we'll note that there are 2 components of the acceleration of point A, a tangential component and a normal component, both of which are drawn over here. In each case, a cross product is involved to calculate each of those components. For instance, for the tangential component, it is a cross product between the angular acceleration of the link 2 with the absolute position vector of point A. The direction of this tangential component is similar to how we establish the direction of the velocity. In other words, if we have the angular acceleration going in the clockwise direction, it will point in that direction, and if it is going in the anti-clockwise direction, it will point in that direction. The normal component is determined by 2 cross products over here, the first of which resembles the velocity value over here, and we then take the cross product of that value with the angular velocity. The result is a vector that always points to the center of rotation as shown here, regardless of the direction of the angular velocity. Let us now look at the motion involved in the connecting rod or body 3. What we notice about the connecting rod, which is different from the crank, is that it is not connected to any kind of frame, and so we therefore cannot use absolute vectors. In this case, we need to describe the relative velocity vectors. The relative velocity vector is written in the same way as we wrote the relative position vector, in this case v, b / a, and is read as the relative velocity of b with respect to a. In this case, the relative velocity vector is calculated by taking the angular velocity of the connecting rod or body 3 and taking the cross product with the relative position vector of b with respect to a. The direction of this relative velocity vector is again determined by the direction of the angular velocity like we did before. We can then use this formula to relate the absolute velocity vectors of pin A and B using the relative velocity vector. In words, the relative velocity of B with respect to A is measured by someone that is moving with the connecting rod. So if the observer is sitting at point A, then it will see B as only rotating around point A, and therefore we're able to use this formula to work out what that relative velocity vector is. The motion of the piston is a lot simpler to understand given that it experiences only rectilinear translation. In this case, point B can only move up or down, and therefore the velocity and acceleration vectors only have J components, in other words, only have components in the Y direction. Let us now confine our attention to the piston motion. As mentioned earlier, the piston undergoes what is known as rectilinear translation. We can observe this by looking at the position vector RB, which can be only written with one component in the J direction. In other words, its position coordinate is only in the Y direction and can be represented as Y subscript B. Using trigonometry, we can work out what this position coordinate is. In other words, what is the distance of the slider with respect to the origin for various input crank angles or theta shown over here. R is the length of the crank, L is the length of the connecting rod, and again theta is the input crank angle shown over here. If we had to insert various values and we plot this position coordinate of the slider with respect to the input crank angle, we end up with the following graph. If we take the time derivative of this position, we end up with the velocity of the piston or the slider, and we can obtain this by using this equation over here. If we plot that again for input crank angle, this is what we see. If we take the time derivative again, we end up with the acceleration of the slider using this rather more complex equation, where now we have phi as a new angle as defined over here. And again, if we plot that for various input crank angles, this is the graph we obtain for the acceleration of the slider. This animation over here shows the position, the velocity, and the acceleration of the slider for various input crank angles. There are two positions that are of interest to us, including the top dead center and the bottom dead center. The top dead center occurs when theta is equal to 0 or 360 degrees, and it occurs when the piston is at the very top of its stroke and is the furthest away from the crankshaft or pin 0. At this instant, the velocity of the pin is 0 and it is busy changing direction. The firing of the spark plug, which causes exploding gases, happens very close to that point. The other point that we want to look at is the bottom dead center, which occurs at theta equals 180 degrees, shown over here in the middle of these graphs. This occurs when the piston is at the very bottom of its stroke, shown here, and closest to the crankshaft or pin O. At this instant, the piston has a 0 velocity as shown over here and is busy changing its direction to go back up. The equation that I showed you earlier for the velocity and acceleration can be quite complicated. For example, let's take the velocity of the piston and look at its exact equation shown here. We can simplify this equation by using a trick known as the Taylor series expansion. This can only occur when the ratios of R over L, or the ratio of the length of the crank over the length of the connecting rod, is very small, which happens to be true for certain car engines where the ratio is between 0.1 and 0.25. When this ratio of R over L is very small, we can apply the Taylor series expansion. If we apply the formula for the Taylor series expansion, which is given here, on the denominator part over here, we can get the following simplifying result. We can do this because we can ignore all the higher order terms for small values of R over L. If we substitute this value back into the original equation for the position and we then take the derivative with respect to time, we get a new approximate function for the velocity of the piston, represented by this equation. This approximate function is a lot easier to handle than the original exact equation as shown here. However, we might want to know what kind of error we introduce by using this simpler function, which is an approximation of the velocity of the piston. To do this, we need to do an error estimation. For example, we could take the absolute percentage error, which is obtained by taking this formula. This animation over here shows how the exact velocity and the approximate velocity differ for various R/L ratios. The differences are captured using the absolute percentage error equation shown here. Each new line that you see over here appears for a particular input crank angle. If we take a snapshot of this, we would make some observations about our error estimation. For example, let's look where our percentage absolute error is very low, which is in this region over here. If we expand what that looks like, we end up with this graph here, which shows the percentage absolute error for various R/L ratios. And what observations we can make is that the error remains quite low, in other words, less than 0.4%, if we stay within those low R/L values, as quoted before as being between 0.1 and 0.25 for typical car engines. However, as our R/L value increases, as we move to the right on this graph, we notice that our error increases quite significantly. The reason for this is that we can no longer neglect those higher order terms because they no longer are negligible and they actually have sizable contributions to the Taylor series expansion. And furthermore, the further away we are from the center point of analysis for the Taylor series approximation, the greater our error becomes. In this case, our center point for the analysis was an R/L value of 0. So as we increase away from that, you can see the error drastically increases. Knowing this helps us understand whether or not we can make certain approximations and what kind of error we can expect by using the simplified approximation.